Okay. So again, your homework, your midterm is up. It is due in 3 weeks. 3 weeks from today. Coincidentally, someone's got to turn off their speakers here. In 3 weeks, I will be at a conference again. Okay. Again, I'll play the same thing. If I can, I will do a virtual class that day. Chances are, I may not do anything specific that day. I don't know. I'll have to see where we are. But I could use it to answer questions on the midterm. You know, if people need an extra day or two, but hopefully 3 weeks is enough. Maybe. I mean, I was able to complete the exam 3 times, so I got it right on the 3rd try. So 28th Saturday? Oh, it's really supposed to be the 26th then, or whatever, ish. Okay. So that now it's hard date, no ish, on that Saturday. Okay. All right. You can tell how I really work on dates, right? It's like whatever, as long as it's done. All right. Okay. And also part of the university, if you are feeling sick at any point in time, you do not have to come to class, you know, et cetera, don't get anybody sick, blah, blah, blah. Wash your hands for 20 seconds, at least 16 times a day. And if you need to, we'll hold the Zoom. I'm going to do my best to make sure that the recording works. If you guys, if someone can test it, you know, with their phone or whatever, make sure it's working, great. I need you to be on top of whether it's working or not. Because I hit the button, it looks like it's working, but I won't know until someone tells me I can't hear it or it's not recording. All right. Where are we? We're at module 5. Okay. We don't do that first. Again, inside some of these modules are papers that might help you understand how people are using the various tools, which is a good thing. All right. And data mining. Okay. Any questions at all on anything? Nobody's got any questions? Sure. Nobody's got any questions. Everybody's okay with the homework? Y'all handed it in today? You got no problems? Yes.
I have some questions.
Go ahead.
In the third problem,
Yes.
the card data has errors in it.
Yeah.
Are you excluding that column?
Which column?
It was the car names.
Okay, so
Parsed out text to 3 columns.
Correct.
Has a quote in it.
So what do you think you want to do with it? Notice, I didn't say what I want you to do. What do you want to do with it?
I was trying to replace the values.
Okay.
But I couldn't replace the values because it has that quote in it, and I couldn't figure out how to replace it with the quote value in there.
Get rid of it. You won't need it.
The whole column.
You don't need the whole column because the whole column could be split up into 3. But if you think about it, each one of those is a separate car. The only field you probably could have used if you wanted that regression was the model, like Ford or Chevy or something like that. Because otherwise they're all too specific, yeah. Right? And you end up with 1 per row. So the reality is that you may say, I don't necessarily care about the model. I'm only concerned with the attributes of the car. Well, if you have the same attributes of the car, cylinders, horsepower, blah, 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 all that other stuff, should the model matter? Should the model of the car matter? No, because it's just a name, right? Unless you believe something is different. Now, what we might do is we might include that variable into the mix, and we hope that it is not significant, right? Because if it's not significant, it validates that theory or that premise, right? That's the way you handle that. Notice, you're not going to get perfectly clean data. So you ask questions about it. That's the key, is learning to ask questions about the data. How many of you think I know what I'm talking about? Raise your hand. If you didn't raise your hand, you're probably right. I don't know what the hell I'm doing. I get a data set. I'm asking a ton of questions of my clients, right? I am asking a ton of questions. I'm not giving you nice, clean data sets because that will serve no purpose for you. Okay? I mean, I can give you a nice, perfect data set and it'll just work and be done and you can be done with your homework in 10 minutes. That's not what you want. No, we'll take that. You want to deal with these issues so you know what to do. Okay? That answer the question? Good.
I have another question.
Go for it.
You said run the linear regression, identify the important variables. Are those just the ones you included within the model?
Those would be the ones that end up being significant. Okay? So if you're running a regression, if you remember from band 203, and if you didn't take it, you need help, let me know. You have to basically run your model with all your variables. Then you can take them out one at a time if they're not significant, right? This is known as a stepwise regression. You can use a step function inside of R. I don't necessarily recommend doing it because you should make the decision as to what variables you're going to remove, right, in the mix. Okay, I think it's a better approach. Some people disagree and say let the model run. In fact, Amazon and Google, when they do linear models, that's exactly what they do. They try every single combination. Why do you think I have a problem with them trying every single combination and giving you the best model? Anyone want to take a guess why I got a problem with that? Yeah.
Might not explain what.
You might not even explain what you're looking for. I could find a great correlation between two variables, and it has nothing to do with what I'm looking for. Okay? But Google plays the black box. Give us all your data. We'll give you the result, tell you what the best model is. No, I want to know why. Oh, well, we can't do that. Machine doesn't do that. Okay? You'll see that when we start dealing with neural networks too. Any other questions? Yes.
Are you still going to go over the loop code because on your optional question, I just did it, like redid it every time with a new row.
Which one was that?
That was the one where you told us to iteratively add a row to the training data and remove it from the test.
Yeah, let me see if I'll do that at the end of the class. Okay? You're not graded on it, so don't worry about it, right? That's why I said optional. You don't necessarily get extra credit either. I'm not a huge fan of extra credit because I make mistakes on numbers, like, you know, get a 9, all of a sudden you get a 10. Good with that? All right. Any other questions? Yes.
So for, I guess, question 2E about running your factor analysis with 3 rotations.
Yep. With 3. Oh, yeah. Okay.
So I did the 3 rotation with the 5 factors. Am I just determining which factors?
Which one you want?
Which one loads on which factor?
Yep. Which is the best model? I just want to know that you ran all 3. Give me the results, and then whatever your final results, whatever the best model with the rotation, that's what it is.
Subjective.
Huh?
So very subjective.
A lot of this is subjective, right? Now, there's an objective component. I mean, I can tell you, here's the thing. And in your project, when you do your project, I may say, why'd you do that and not this? What were the loadings, right? What was this? And you should know the answer. You should be, and one of the tricks I'll tell you is this. I tell this to my team as well. When you do a presentation for a client, for an executive, for a customer, whatever it is, you should know the questions they're going to ask before they ask it. How the hell do you do that? You and your team should be asking a ton of questions. He could ask us this, she could ask us this, we could ask that, they could ask this. You need to have the list of questions for every slide. You should come up with critiques of each other slide. Well, what about if professor asks this? What about if he asks that? Do we have an answer? That's how you're going to know you're going to do well. Okay? How many groups did I say there were here? 4 or 5? 5?
We have groups of 6, so 20 students in class.
I have no idea. It keeps fluctuating. I think it's 20. 4 groups, right? 4 with 7. Okay. All right. So if it's 4 with 7, we can all do it on the same day. I think we talked about that. Okay. Cool. Any other questions? No? Okay. So we briefly last week talked about supervised and unsupervised methods. Again, the supervised method are the methods that we have a known response variable. We can train our model. We could say we're going to run a linear regression. We know what the results are. We find the good model. We fit to that training model, and then we'll test it against the test set that it hasn't seen.
Unsupervised algorithms are going to be algorithms that deal with things like clustering and association, in which we don't know anything about the data. We're going to deal with the first one tonight, which is KNN. In classification methods, which is what we're focused on in this section of the lectures, classification, I want to classify customers. I want to classify them in terms of high value, medium value, low value. Marketing companies love to do this. Why do I want to classify my customers into medium, high, and low? Yes.
So you know how to market.
So I know how to market. I know the attributes of folks who are going to be high value customers, so I can maximize my marketing spend on those people. That is exactly why we do classification. We also might do classification who's more likely or less likely to have coronavirus, right? We literally take all of the attributes. Who's susceptible? What type of case is it going to be? High, medium, low, something along those lines. We have a number of methods to do this. We're not going over all of them. I'm giving you some of these so that you can, if you're interested, you can either go on your own or you can ask me. It's either way. Logistic regression, we don't cover in this class. We cover this in band 250. Great technique to literally do a 1 or a 0. It's also similar to do an ordinal, 0, 1, 2, 3, 4. It's also used for Poisson, which is small count data. Naive Bayes classifier. I love Bayesian algorithms. They're fantastic. I'm not a super expert in them. I love them and I keep working with them because what it does, Bayesian classifier, if you take Bayesian probability, is all about having some distribution of probability that you think is going to happen. What is the probability that you guys are going to win next week in your next game? 50-50. She's doing a uniform distribution. Look, I'm taking this whole thing into like distribution right now. 50-50 uniform distribution. And now what we do is we start playing games and we see whether or not they win. As more and more information comes in, the probability begins to shift until it doesn't shift anymore. No matter what you do, it pretty much stays at some theoretical saturation point. We're done. And Bayesian algorithms do this. So Bayesian is all across the board. One note about Bayesian is this. There are two distinct camps. They're like religions in statistics. The Bayesian folks and the frequentist folks. Very much like what you're about to see for the next 6 months with the Bernie Sanders folks and the Biden folks. They're going to be at each other's throat. The only difference is in statistics, they write papers and it's kind of boring. Anyway, so those two methods, you can do all of the methods that you're going to learn in some way, form, or fashion using Bayesian methods. And that's a very simple formula. The Bayesian formula is very, very simple. Support vector machines are, again, a form of classification. They create these very, very complex, what are called hyperplanes, which is just a line in multiple dimensions. Decision trees we will do. We're going to just create these if-then branches and figure out what some numbers are. Random forest does it kind of takes random trees, if you will, decision trees, and aggregates them together to figure out what the best set of trees are. We don't do that. Neural networks we will do. We're actually going to do a handwriting analysis, but you can use neural networks both for classification as well as regression. And K-nearest neighbor, which is the first one we're going to do. Don't ask me why they're in this order, but I could lie and say it's because since that's the last one, that's the first one we're doing. I could make it up. So talked about logistic regression already. Naive Bayes classifier. You can read these. This is what your decision trees look like. Random forest. Neural networks, which is really cool. We create these layers and stuff. We'll go into detail on this. K-nearest neighbor, which we're going to start with. This algorithm is what we call, someone who joined in has to turn off your speaker. Thank you. Nope, still on. Thank you. All right. So in K-nearest neighbor, what we do is this is a supervised algorithm where we basically know where people are. We know certain customers are high value, low value, medium value. Yeah, something like that, right? We get a new data point, and we want to know exactly whether or not it's probably going to be a high value, medium value, or low value. So these purple points here on the screen, let's see if I do this right. These purple points, okay, are new observations. And we want to figure out what we're going to classify them as. So in this case, how would you classify this purple? Would you classify it as blue, orange, or green? This top point. What do you think? Blue. Why would you classify that as blue? Because it's closer to all of those. Correct. What about this one? What would you classify it as? Orange. Same reason. And this one? Green. Even though there's a couple of oranges in there, right? Now, what you did was you observed and you said, well, it's closer to the blue points, it should be blue. It's closer to the orange, it should be orange. There's more greens, it should be green. That is exactly how this algorithm works. It works by taking the nearest neighbors, k nearest neighbors. What is k? However many you want, 3, 4, 5, 10. And they vote, kind of like a caucus. They vote, they walk in and they say, I'm voting for blue. Why? Because I'm blue. Or I'm voting for orange because I'm orange. Whoever gets the most votes, that's who that point gets classified. It is as simple as that. The algorithm runs it for you. Where am I? I'm here. So let's go into it. Why do we use this? It is one of the most widely used algorithms because it's so simple to run. Okay? It is very simple to run, and more importantly, it assumes no specific parameters or distribution of data. It doesn't matter whether it's normally distributed. It doesn't matter whether it's exponentially distributed. It makes absolutely no difference. And this is a key advantage since the data does not need to conform to anything. If you're doing regression, right, linear regression, we have to have the residuals to be normal. Not necessarily every data point or not necessarily every variable, but the residuals have to be normal. Now, for you on the homework, we did not do that. I didn't give you that because I'm assuming that you've done 203 and you know how to do it. If you want to learn how to do it, I'll give you the code and I'll show you how to do it. It's something you should know. Of course, if you took my 203 class in Excel, you should know how to do this, but I don't know what we remember, right? It was a long time ago. KNN, though, is a lazy algorithm. Kind of like me. I'm lazy. I like being lazy. Lazy algorithms do not use training data to do generalization. I don't train and then do test. I just use the whole data set, okay? But I'm using the whole data set to tell me about the new observations. KNN uses all of the data for training, and every time I get a new observation, I throw it in and it basically uses it again because every single point begins to vote. Therefore, it's an excellent choice for classification when there is little or no prior knowledge about the distribution and you just want to explore. It is an exploratory technique to figure out new observations where they should reside. But if you think about it, if I've got a new customer coming into the website, I know their browser, I know the IP, I'll know the geolocation, I can know how many minutes they spend, I can know where they attend, I can, every single thing that they do, begin to classify them. I can say it's probably this, probably this, probably this, going to be here, and get closer and closer and say, boom, now I've got my final classification. Now I'll send them a new coupon because they'll probably buy. Wrong computer. How does it work? We said that these items should be close to each other, right? So those purple points were close to the blue area. The other ones were close to the orange area. Well, this basically uses distance formulas. The most common distance formula, everybody knows. They have it basically as part of their nightstand with a nice picture of Euclid, the wonderful mathematician, because we have nothing better to do. What is the distance formula? A squared plus b squared equals c squared. The old Pythagorean theorem. I like that. It's good to know. Good to have that around. You never know when it comes in handy. This is my square root. This is the rise over the run. Here is my new point. I'm calculating the distance between the purple and the green and the purple and the blue. Whichever one it is closer to, I am more likely going to be like. That make sense? That's in 2 dimensions. Does it work in n dimensions? What do you mean about n dimensions? This is like Star Trek or something. Space-time continuum. Every variable is a dimension. So this is a 2-variable setup, y and x. But if I have a 3rd dimension that may go like in a diagonal this way, right? That would be a 3rd dimension. And a 4th dimension. You can't visualize it at that point, unless you've had a little bit too much to drink, in which case you can visualize anything. The whole point is that every single variable we have will follow this formula. Do you have to do this formula? No, it does it for you. But we're on computer. Once we figure out the distance, if I only use 2 points, I basically am saying, well, whoever's closer wins, but that may not be good enough. I like having democracy. I want to have multiple points, have a vote, but not everybody. That's why we call them super delegates. A lot of political things there. They're a debate on or something. You'll get a laugh, it's about to get real fun. So what we do is, if k is equal to 3, then the majority of vote of classification objects will be used. If 2 of 3 closest neighbors are given, then the new observation will be, or green will be green. So this point is close to here, here, and probably this one, right? 2 green, 1 blue, therefore we vote green. That's the way it works. So one of the key things is going to be, how big should your k be, and what should k be? K really, there's nothing against it. K should be odd. K should be odd. Because if it's odd, you'll always have a +1, right? But if it's even, you could have a tie. And then what do? There's nothing that says it can't be even, but generally it should be odd. If KNN is used for continuous prediction, then the value given to the object will be the mean of the, or median of k nearest neighbors. In other words, not used as a classifier of either green or blue, but used as the prediction of some value, like how much income. You would take the income of this, we do it this way because I know people are online. You would take the income of this point, the income of this point, the income of this point, and average them together to get the income of that point. That would be your prediction. That make sense? Okay, that's one way to do it. Most of the time, KNN is used as classification only. Okay, it's much easier and it's more simpler to understand, but it's a predominant algorithm for this. I would not necessarily use KNN for a continuous prediction, but it's possible. How do we use it? Credit ratings. And risk. Yeah, credit ratings. Whether you are a high credit risk or a low credit risk, they use KNN. I can use the credit ratings basically to examine characteristics, and with the premise that if your characteristics are similar to people who basically default on their loan, there's a good likelihood that you too will default on your loan. And banks use this. They use it quite extensively. The reason they use it is because it is extremely quick to run. I don't need to run massive amounts of computations to do this. It can run extremely quick. Voting preference, classification of a potential voter to determine whether they will vote for a particular party or person. It's used also quite a bit to classify who I want to go after in terms of parameters. I can figure out who I'm going to send that advertisement to see if I can get a vote. Didn't really work for Mike Bloomberg. Wow, nobody's chuckling at this, man. I thought that was, huh?
It's too sad.
It's too sad. Too sad. I thought you were going to say it's too soon. Character recognition. It can be used to determine whether a character is a certain letter or not, based on the parameters. We can use this to say, if you have these attributes of the letter, individual pixels, which we'll see in neural network, it is going to be an A, it is going to be a B, it is going to be a C. So it can be used in a variety of different ways. How do we choose K? This is a trade-off between speed and accuracy. The larger the K, the longer it's going to take. Okay? Now, not tremendously long, but it's going to take longer. If you're dealing with thousands and thousands and thousands of predictions, it starts to add up. So in general, we want to choose a small value for K. 3 is generally an okay number, no pun intended. It's an okay number. 5 gets better, 7 gets better. When you start getting to 9, 11, 13, you start increasing the computational power or the computational requirement. When K is small, like 1, it returns the classification of the nearest neighbor. This leads to overfitting. Okay? This is an overfitting thing. If I were to take one of the data points in my training set, plug it back in, it's going to give me that exact value, right? If K is too large, localized behavior is ignored. In other words, what will happen, let me see if I have it on the next slide. Nope. In this example here, if I use all of the data points, let's say 1, 2, 3, 4, 5, so this is a K5. What happens is that, and imagine if you had a ton more points, all of these observations far away are now included in the classification, right? Trying to figure out the number of items that are close to it. That becomes a problem. The reason it becomes a problem is because, first of all, I got 2, 2, and 1. So this is a scenario where you have odd, and I'm going to have a 2, 2 preference. But the localized behavior, this cluster of green that's occurring here, is overshadowed by a few points that are further away, because they now get a vote, and they shouldn't. Almost like someone in New York getting a vote in California. If it's too big, you're going to cast a too large of a net, and that localized nexus is going to be a problem. So you want to be careful of what you choose there. Okay? Does that make sense, KNN? Cool. Let's go through an example. In your R code, I have to find it now. In your R code, you should have K nearest neighbor. We're going to load up this data set here called glass. Okay. Now, here it says could not find function read CSV. It's not my computer, that's why. What does that mean? Cannot find function. What does it mean? What? What? You need to install something. Okay. I can tell you that if I look here in the import data set, it's going to be reader, R-E-A-D-R. So let me just install reader. The data set's on a URL already. Just run that line after you've installed the reader package. And it should run, which it does. Okay? I know some of you struggling with R, which is perfectly fine. Just keep working with me and you'll get through it. R is cool. You know why? It's better than Q. Stupid. I can't help it. I got a ton of stupid jokes too. Huh? You run the first line, yeah. Yeah, because that's going to pull the data from that URL. Some data I will give you, some data will pull from a URL. By the way, if you ever work with Amazon S3, that's how you're going to pull data. You don't necessarily want to download it. You want to actually put the URL, and you can actually get the data. Because you do not have a package, right? Make sure you turn it on. Yep.
When you're using a URL, you need Wi-Fi or any channel.
Otherwise, how are you going to get it, right? Okay. Good. And the reason I'm okay with it is because usually everywhere you can kind of like get signal. You can kind of rip it off of people's houses too. Like you're driving by, just turn it on, watch someone pop up. They'll be unsecured. You're golden. You're having trouble. Did you install the package? Reader, R-E-A-D-R. Did you turn it on the right? It says library. What error are you getting? Did you just run line 1, or did you keep running more? It's in the R code. Just run line 1. Here, this right here, knearest.r.
Yeah.
Okay, so you should get this file.
It doesn't open.
If you download it, just go into RStudio and do file open. No, don't do that. You're trying to import the data set. I don't want you to do that. What's wrong? Open up the file itself. Close that. Yes, close that. Go up to File. Open. Find your file. And open that. There's your file. Now you can run that. Okay? All right. So I also give you some description that comes from the website itself. ID number 1 to 214. How many observations do I have? How many observations do I have? 214 with how many variables? 11. So I'm going to do a summary. You know why? Because that's a great thing to do. What am I looking for? Oh, crap.
Where it went.
Yeah, that's true too.
We're looking for bad columns.
Correct. Oh, where's my view for the windows? Because I killed it somehow. View panes. I want zoom, source, view, panes. There we go. Thanks. Summary, class. Anything I need to be worried about this data set?
Maybe X9.
What's wrong with X9?
It only has one value that's not 0.
So let's take a look.
Or it's got a number. It's got like 25 values of 0.
Excellent. I like that. He's like, you know what? X9 may have a few, 1 or 2, right? It's got 1. What did you say?
Well,
25. Okay, watch. So 25 of 215 actually have values. The rest are 0. You need to make a call as to whether you're going to keep that or not, because it could affect some other things. Okay? I could also create another variable that has a 1 or a 0. In other words, instead of actually looking at the numbers that I have of the 25, I will have 190 that are zeros and 25 that are ones, and now it's just a binary 0, 1 to try and consolidate that information. Okay? This becomes your call to kind of do. Once you've got that, and you basically, I'm looking for nulls, maybe I'll look for outliers, and so forth. I basically have assessed whether or not I can work with this data set. Does that make sense? Now, from an R perspective, specifically, you don't have the names of the variables, number 1, okay? So I've given them to you, and if you look in line 25, I run names of the data set, and I pass in a vector of the actual column names. Do you see that? Because the data set right now says X1 through X11. So you'd have to know what those columns are. You can get that on the documentation for that data set, or we will actually, separate one. Yeah, we could actually use this 1 through 11. So I will run this. I'm running line 25, and then you will see it has now given me the names. Now looking at this, what do we think we want to classify? Which variable? Which variable do you think we're going to want to classify? Type. Type is a classifier because it basically goes from 1, 2, 3, there's a couple, there's no 4s, there's a 5, a few 6s, and some 7s. Does that make sense? So what I'd like to do is run a KNN, K nearest neighbor, to take the other attributes and predict what class it will be. We good with that? Okay. What column don't we need? We definitely don't need the ID. So we're going to get rid of that one. And whether or not you get rid of, what was it, number 9, which is FE, Huh? Which one was the one? Sorry. BA looks like it has data. BA, okay. Yeah, BA was the one that only had 25, right? Which is what, barium? Barium. Cool. Now, the only other thing is when I imported it, do you see how it imports like with this red stuff here? Okay. If you run glass by itself, the name of the object, you're going to see that it tells you that it is a Tibble. Okay? It's a Tibble. I don't want you working with the Tibble because some of the functions don't work well with Tibbles. Line 27 will convert your Tibble to a data frame. Now glass is just a data frame by itself. And now we're ready to work. Make sense? Okay, and if you run glass now after I ran 25, you will see that it looks like this, which is my data frame, my traditional data frame right there. Okay. All right, going back to this. So we've run our summary. We know our 9 variables. Key to the analysis is going to be these. Whether we keep that 9th one or not is barium is up to you. The elements BA and FE could be problematic. I don't know why I didn't put that 3, 6, 8. I forgot to put the 9th one here. So what I can do is I can plot each one of the variables against each other. I can just plot them, right? In this case, I'm plotting sodium and Ri. Anybody know what Ri stands for? What is it? I have no idea. It is the refractive index. Exactly. Thank you very much. It's just testing. I'm just comparing the two. I want to see where they lie. I want to see what moves together. Okay? Anything that seems important or not, or I can get rid of things. There's no particular rhyme or reason. I'm just showing you how to do a plot. So in R, you're going to see this here. This is my ggplot. Remember we talked about ggplot a couple weeks ago, right? So we'll start using a couple. Here, I'm going to do a ggplot. ggplot, like I said, is a little bit more difficult than the standard plotting features in R, using just plot. It takes a little bit of time. So if you're designing a chart and it runs into a problem, just let me know. Okay? I kind of start looking at the different parameters because they've changed it once, which threw me off completely. But I look it up all the time. Okay? And I know what I'm looking for. The first parameter is the data frame. It says, I want you to plot the elements of the data frame. The second thing is this thing called AES, which is aesthetics. This is the look and feel of the plot. The X value is going to be NA. The Y value is going to be RI. These are the variables of the data set that we passed in. Does everybody see that here? So we're passing in for X. On the X-axis, it's NA. On the Y-axis, it's RI. We're good with that? And I'm passing in another parameter, which is the color. It's British, because it has the U. Color. The variable is going to be type. So the type, I have 1 through 7 types, right? That will be the color of whatever point it is, or the point will be that color. It just assigns 7 different colors. If you want to change the color palette, you can do that. It's a little bit more complicated, but right now it just chooses 7 colors for you. Then I have this plus. Why? Because what it does is it creates the plot, and now I add additional attributes to the plot. So the first one is geom point. I want the data points to be points. I don't want lines. I don't want bars. I don't want histogram. You can do any number of those. Then I'm adding to that plot a title, GG title. Reflective index divided by sodium coded by type of glass. That's just going to plot right on the graph. I'm going to run this. Cannot find function ggplot. What does that mean? I need the package. So I go and install ggplot 2. Can you tell where I got messed up? I was ggplot1 and then they changed it on me. Swear they did it on purpose. The best was in my multivariate statistics class. They literally changed a package the day before my class. You could see the thing was like February 24th. I think it was last year or the year before. February 24th, and my class was on the 25th. I was like, you gotta be kidding me. You changed this yesterday, you couldn't wait 2 days? But I'm glad they did, because otherwise the students would have had a ton of problems. So. All right, so we gotta wait for this. While I'm waiting for that to load, let's go back to the PowerPoint. Okay. So what we're going to do is we actually will create a new data frame. Okay. That new data frame is going to have new observations. I want to plot 3 new points that are coming into my KNN. And what's really cool is this. This function here, from here to here, is what actually will run the KNN, just that one line. There's no multiple lines, no cutoffs, no communalities, no loadings, no eigenvalues, none of the things that have given you nightmares over the last 2.5 weeks. All right, am I good? That's about right? Headaches, nightmares? None of that. We just run it and it gives us the answer that we need, which is very cool. So this part here is new data set. So we're creating a new data frame. Look at the columns. I create an ID column, an RI column, an NA column, an MG column, and each one of them has 3 observations. So I created 215, 216, 217. Then it's going to have 1.5, 1.5, 1.5, 13.4, 14.5, 15.5, etc. I'm going to show you this when I run this line of code. Let me do it now, actually. Let me go back to R. Okay, that's done.
Where did you get this out?
I made them up. These were, I had to make up some data as though we got new data coming in. If you had an Excel spreadsheet that had new ones, you would import it and you could pass that in. In this case, I made them up. For your, I gotta remember, I think for your homework, not homework, for the midterm, you can take 3 out of the data set and use those as new. Okay, so you don't have to create anything. That's not, the whole point is not to create data. I mean, you could do that in any Excel class. So let me run the plot while I'm here. Of course, cannot find a plot. If it says cannot find it, the package is loaded. I can turn it on because I didn't turn it on. I run it. Here's my plot. It's nice. It gives me the shaded regions because in this case, it's set up to be shaded. You can do it where it's not shaded. It's entirely up to you. And it tells me that, you know, where these items are loaded. Okay? If you play around with ggplot and you need some help, you want to do certain things, just let me know and I'll give you a hand with it. All right. I come down here. This is the data frame that I was just talking about. Right? This new glass data frame. I'm going to run it. Oops. This is an extra parenthesis. You do not need that. So I run 45 to 56. Run. Notice it gave me a new data frame, 3 observations, 11 variables. Notice I have 215, 216, 217. I'm just matching my data frame. When I look at this, 215, 216, 217. Each row has the first row has the first value in each. Second row has the second value from each, from here. 215, 1.516, 12.55, and so forth. You look at your new glass data set, here's your 215, 1.516, 12.55, and so forth. Okay? Does everybody see that? I made a new data set. Now, for KNN, I actually have to create a vector. I have to create a vector of the types. Okay? I have to create a vector of the types. So what I'm going to do is, and I think, yes, I missed one line, but I'm going to go back to it, okay? Because I'm going to show you what happens. The type is the variable that has our classification, correct? The type has the variable for our classification. So what I'm going to do is I'm going to put that into another variable. I'm going to separate it out so that this vector has all of the classifications in it. That's all the true class does. And again, it can be called whatever you want. Here's all my 214 types from the data. So observation 1 is a 1, observation 2 is a 1, observation 3, all 214 types. Make sense? Okay, I just want to separate it out. Why? Because KNN is going to have 2 different parts, right? So I'm going to send the data in one, I'm going to send the classifications in the other. Could I have done it combining things? Yes, but it's easier for me to demonstrate it if I split it out. Okay? Now I'm going to run the KNN. So there are 1, 2, 3, 4, 5 parts to this, to running this model. The first part is the data. So you're going to see the data here. KNN, this is the data. Now, this basically says glass bracket comma C2:10. What is that? Someone interpret that in English for me.
That's all
Yeah.
the glass columns that aren't ID,
Right, which numbers?
2 through 10,
2 through 10.
and aren't typed. So this type is 11.
Correct. So what I'm doing is I'm passing in the glass data set, right? I open the bracket. Is there anything before the comma? No, if there's nothing before the comma, what does that mean? All the rows. Those are all the rows. So after the comma is the columns, but I specifically told it only use columns 2 through 10. I've excluded the ID because we don't need it, and I've excluded the type because I'm not using that for the classification. I'm going to use that a little bit later. This is just the data points that will be used to analyze distances. Does that make sense? We're good? Awesome. The second one is the new data. So the second parameter is my new data. Yes?
So we can use this way to exclude the columns in the beginning and the last one.
Yeah.
But what if we want to remove the middle one?
Then just you have to do C open parenthesis like 2:5 comma 7:10. Okay, you just got to create a vector of the numbers that you want. You could have done C 2, 3, 4, 7, 8, 9. Okay, you just create a vector and pass it in, and that's what it will do. Okay? Yes?
The top right, two glasses with data, and then you have those numbers. So for example, ID equals 250.
Yep.
270.
Yep.
What do those numbers represent?
This is new data that I'm going to send in to be classified. And it's this. You see this new glass here that I created? Give me 1 second, I got to get out of this. They look like this. Pretend that this is new data that came in, and I want to know what type it would be. Okay? Make sense? Any other questions? Yes? No? Good? Yep. Go ahead.
What is the function of the library class command that you have in?
Give me 1 second and I'll tell you. In the R code, right?
Yes.
You'll see in 1 minute. These 3 observations are going into a data frame because I want to classify it. Pretend this is new data. Someone comes over to you and says, hey, I got some new data for you. Can you tell me what class it's going to be? And boom, you can tell the class.
So when we do this code here, 217.
It'll be what?
217 instead of 214. Pretty much merging.
Well, technically, I'm adding new IDs so I can merge them together. Yeah, so, but you said the word class, so I'm not, there's nothing to do with the class here. Huh?
Observation.
Yes, observations, correct. Yep.
I have another question about why did we add type types to the records if we're trying to figure out what types they are?
Because we're going to first take all the data with their types, right? And oh, you're talking about here?
The new.
Okay, so you didn't need to, if you don't want to. But what I did is, I think they're 3, I think they're 4, I think they're 3, 3, 4. I think. So when it gives me the prediction, I'm going to see if I was right. Did I need that? No.
Is there a way to do it without providing a type?
Just get rid of that column.
And will it build?
It'll still give it to you. Okay?
Still not taking it to the data point that you're analyzing.
Bingo. So if you look here, you see this down here? Look at that. In the new glass, I didn't use it at all. I put it in there because this happens for real, right? People might go to Andy and say, Andy, I got this new data, and I think it's 2, 3, 3, 3, and 4. But Andy, being the top-notch Hofstra data scientist he is, says, no, I'm going to run a KNN classifier, and I'm going to prove whether you're right or wrong, because we accept nothing here at Hofstra without proving it by science. And you're going up against a couple of Harvard folks. You got to win, okay? You got to represent. Because our lacrosse team ain't doing so well, from what I understand. You didn't understand which part? Okay. So your new data has 11 columns, right? And it has the type. But if you look, when I'm passing where the red underline is, I only pass in new glass, bracket, comma, C, 2 through 10. I'm not including that 11th column nor the first column. Because up above, the line above it, it doesn't include the type, it doesn't include type or the other. I don't want it, right? The only reason I provided it in the sample data set was because we think that it's type 3, we think that it's type 3, we think that it's type 4. But we're going to let KNN tell us, and then we'll match it, we'll see if we were right. Okay? Does that make sense? I'm not qualifying whether the 3, 3, 4 are correct. We're just, someone came over to Andy from Harvard, okay, and said it was 3, 3, 4. So to you to prove them wrong. You're the only thing standing between us and the reputation that we hold. Yeah?
Type not column 11, that not being included with that?
It's not being included because it will actually be included in the next line as true class. We're going to tell it the observations, the 214 observations that you're going to train will be from in true class.
No, it's just what you're like loading for it. It's like ID obviously is column 1, so
Right.
we're including that.
Yep.
But then is type not
We don't include it as part of the data.
okay.
We will only include it as part of the class, which is the third parameter of the function. Okay?
So but even the first main class data set
Does not have the type.
Okay.
Because the types are represented by that third parameter, true glass. We have to pass it in separately. Yes?
So what was the point of designating the type as factor earlier on?
We're going to see that in a second. Okay? Because I actually haven't run that yet. We good? Cool. So now, the next part is the true class. The true class are the types of each one of the observations in this first part from the data. So in other words, we have 214 observations. I'm passing in 214 types in that third parameter. Okay? This is just the way the function is. There are other functions that take the whole thing. You just have to tell it which column is the type. Doesn't matter. This is the important one. K equals 3. What does that represent? The number of votes, right? The number of nearest neighbors that we're going to look at. So this is what you can change to 5. You can change it to 7. You can change it to 11. Probability equals true. This is going to display the probability. Okay? These are going to be the probabilities associated with the number of people, you know, for this, I'll show you for the observations, okay? In other words, 2/3 of the neighbors voted for 2, and 2/3 of this neighbor voted for 1, and so forth. When I run it, you'll see, yeah.
How do you decide on the K just based on the number of rows in your data set? So if you had 1 million rows,
It's a trade-off, right? So what happens is that it becomes, choosing the K is a little bit more of an art. You'd never really get that high. But it depends on the way, a lot of things, like the way your data clusters together, how many you think you need, what's the localized effect I'm looking for. If the data is very sparse, right, then you may want smaller K, because then the localized behavior will be fine. But if it's really dense around certain points, you may need to increase the K so that you can get a better number. How are you going to determine whether it's good or not? Well, because we know like some data, we want to see how well the KNN did with some new data, right? Almost like a test set, and then even though it's not really direct, if the number works out well, then we did a good job in terms of accuracy.
And by work out well, you mean?
It predicted accurately what it was. In other words, if it predicted a type 3 and it was a type 3, then that's good. If it predicted a type 4 and it was a type 1, that's not good.
So you can use like a test in it.
You could, yeah, you can absolutely throw in a test, but you're going to have to throw in smaller test sets and almost keep it growing because it changes every single time. It's not something that will be static, like a linear model could be static. Yep.
Does the, let's say we run the test with different amounts of K and we get higher percentages for all of our values.
You mean better numbers, right?
Well,
The
a higher
probabilities?
number of neighbors have that.
Yep. You should, again, it's based on the accuracy, right? So it's your hit rate.
Okay.
How many did it, you know, it predicted that you're a 2 and it was a 2, that's good. That's what we want. Okay? You create a small little table of accuracy measures. Hit rate, you know, like a hit rate. Yeah. Okay? Any questions? Yes?
So when you're running the plot, what do you choose as the attribute for color usually? Like if you're doing
You're back on 2 slides before?
yeah.
Whatever is going to
I'm
be the
relating it back to like what we're talking about, using it to make
to make the classification.
yes.
Yes, so that's what we did. The color is usually a factor that allows us to do the color. Okay? Anything else? Okay, moving right along. So let's run this. So I'm going to run the KNN. Now, what does it say? What's the error? Cannot find what? It cannot find function. If it cannot find a function, what does that mean? You need the right package. I looked it up in Google, etc., etc. It's class. I'm going to basically install the class package. We install the class package, we wait, and we're done. We install the library, so it's now loaded. I can use it. I will now run my KNN. And it runs. Good? I will display the model. Sweet. Look at that. So what is it doing? It took the 3 new observations from new data and gave me a prediction as to what it should be. The classification should be 2, 1, 1. Does that make sense? The 3 new observations that I passed in new, what do I call it? New glass, will be a 2, a 1, and a 1 based on the attributes that were passed in. Yeah.
So would you try a different K value because those didn't match your type?
Oh, okay.
Your original type?
I wish you didn't add that last part in, okay? Would I try another one? Yes, because they didn't match the types. You're making an assumption. What's the assumption? That the types were correct. If you knew they were correct, then yes, you could do that. But I kind of told you I made them up, right? It's like a key indication that I kind of did it on purpose. Okay? So that you can see that. By the way, don't ever assume that someone gives you data and it's correct. Right? I mean, you work here at Hofstra, right? How's the data? It's like, oh, yeah, no, it's good because we're being recorded. Yes.
The line 66 means like
66% of the vote went to that class. 2 out of 3. Okay? 2 out of 3. Do you need the probability? No, you don't. Yes.
What happens if it was like, if there's 3, but it's close, like every one of the 3 is different?
Then you'd have a tie. That's where the probability comes in, because now you're like, now I know why it voted, why it got that. It usually chooses like the lowest number in the alphabetical. What I mean by alphabetical is 1, 2, and 3. It chooses 1. Yeah. So what would you do in that case if you have too many ties?
Increase the K?
Increase the K. Get more people to vote! Yeah.
I think you sort of answered my question. I was just going to ask you, what size of K do you use?
You're going to use an odd number. You're going to generally keep it small, somewhere between 3 and 9, 3 and 11. Okay? There's no real reason necessarily to have more, but again, if you have 1 million records, if you look at the data and it's very dense, packed together, you may need more voters, right? If it's very sparse, you're going to need probably less voters because you want to create that localized effect. I want the local people to give me a better vote. Okay?
Can you say that again?
Okay, so if you have 1 million rows, if it's extremely dense, right, that means that you could end up with 3 or 4 very local because it's dense and it's going to be wrong because the items around it are the opposite class, right? And those 3 or 4 throw you off because your K was too small, right? So what you do is you would increase the K to get rid of that effect of the denseness by saying, no, I'm going to leave it dense, but I'm going to add more voters, if you will, into the mix. But if it's sparse and you have, let's say, a large K, then that means if my data point is here and I've got 3 or 5 that are close, but you want 11 and those next ones are over here, all 6 of those could be 1, and guess what? Now it votes for that. Okay? That's the difference between that denseness and the sparseness.
So, I don't know if this is going off on a tangent, but how do you tell the denseness or sparseness?
You got to look at the data. You look at the data and you look at each one of the variables. That's why those plots kind of help. There's other methods that we would use to really measure that. That's more of a statistics thing. Okay? But the answer to the question is that's how we would tell. Okay? Anyone else?
So
Yes.
KNN still works if for the class the attributes is from 2nd to 10th, but for the new class the attributes is like from 3rd to 9th.
No, they have to have the same. You have to have the same variables. Yep.
But because sometimes we can know some attribute value in that case.
Then you either impute it, you're going to have to put something in, or your classification is going to have to be done without that variable. Remember we talked in, I think, lecture 1 or 2 about imputing. What do you do with missing data? That's that exact scenario. I can either pull the column out completely and say I'm not using it, or I can impute data and say, I'm going to choose the average, or I'm going to choose a median, or I'm going to choose the minimum worst case scenario or maximum worst case scenario. Okay? Yep.
So I ran it with 5 and 7.
Yep.
Okay, like they came out with different answers on the first one. So
That's
I don't even know
great.
which one to use.
Oh, that's fantastic. Why did it come out with different numbers?
On one of them, yeah,
Wait, on one of them? On which one?
the second one.
So the other 2 were fine, but that one wasn't. What's going on there? What did you run it with? Which K?
I did 5 and then I did 7.
Okay, so you want me to run 5?
And the probability is lower.
Okay, and you want me to run?
7 has the same thing, so you can just run 5.
Okay, so run 5. So we ended up with 221. The other one was 211, right? You said the probability was lower. Well, again, this is based on the votes, right? So it was 5, so 3 out of 5. Yeah. I'll come back to your question, but
Well, no, you should answer hers first.
then let me answer that one first. Okay. Why did that happen? Why did it move?
Because some of the points that we pulled in now added.
Correct. We're voting differently because this is the exact effect that I talked about with the denseness and the sparseness. In the dense, because our K was too low, those, one observation probably, moved it into a different category. Two observations move it into a different category. You also only have 214 data points, right? You have 214 data points. Again, how many are going to be close? If you've got 5 out of 214, that's a different percentage than 3, right? And this is what happens. Reduce the number of data points from 200 to 100. Watch what happens. Yeah.
So does KNN assume an equal weight of every variable that
Yes.
So if some variables are more important to the type, we don't want to use KNN.
You could use KNN, just transform them.
Transform.
So
Transform
we
them.
just adjust the weight
Yep.
based on the distance.
No, hold on. No, you're saying based on the.
Let's say the amount of iron has a lot more to do with the type in glass than anything else.
Okay, so I'm going to answer it 2 ways. Number one is I wouldn't use KNN. Okay, could you use it? Yes, but what you'd have to do is you'd have to do something to the iron, right, that would lessen its effect, right, by either increasing a distance, right, like squaring it would increase the numbers dramatically, or decreasing it by inverse power or something like that. You could do that. You just can create new numbers from it. You're creating new numbers from FE as long as you're doing something constant to it. Okay. Any other questions? Okay. And that's that by itself is the KNN piece. So what happens then? We have we have the probability parameter. Did I run anything else here? I did. I think we'll do this right after. Okay, I'm going to let you go on a break, and then we'll come back. We'll talk about Euclidean distance. We're going to talk about a little bit about the Euclidean distance here, but we're going to get more into distances in decision trees and something else later on. Okay? Take a 10-minute break. Come on back, and I'll pause this so I can save space. All right. This will probably take about 10 or 15 minutes, and then we're done with KNN. We'll chat and let you work in your groups or ask questions about your homework, etc. Okay? This is one of the easier modules, right? Now, while we talked about KNN and the nearest neighbor, and we had like 3 or 4 nearest neighbors, etc., whatever it is, we actually can compare just the Euclidean distance of a point to another point, whatever it is. Okay, and there's a function that allows us to calculate the Euclidean distance between 2 points, no matter what it is. So the first thing that we would do in order to actually get our distances, because that's what we're going to do, we're going to calculate the distances, is to normalize the data. There's 2 ways that you can normalize the data. One is the function that I gave you called min-max normalization, which will normalize a vector, or we can use the scale function. Okay, now the scale function in R, and we're going to edit the code. There's a lot of extra stuff that I'm just going to get rid of because we don't need. You're going to see here. Just give me 1 second. What we need to do is we actually will need to scale the whole data set. Okay. Now, before I do that, I'm going to combine the 2 data sets. So here, before we do anything, I want you to get rid of line. Actually, I don't even know if I needed to scale it. Hold on, let me just try something. You know what? Yeah, that's right. You don't need to scale it. All right, ignore the scaling part for now because you don't need it. Okay. What we're going to do is we're going to get rid of everything from 70 all the way down to 108.
Including 108?
Yes. Yes. Just delete them. I just ran them. Okay. I also forgot one thing. I gotta go over lines 56, 66, 68, and 69. Okay. After the model, I had 3 additional variables here. Okay. What I did was, or does anyone want to tell me what this does? I want to give it a shot. These 3 lines right here. Okay, they're right after the model. Yeah. What does it do?
You're adding the type that model calculated.
Correct. I'm actually overriding it because there is one there. So the first one, line 67, says for the first row of new glass in its type column, I want you to put the type that it was. So KNN MDL1, right? Remember KNN MDL had the 3 observations, right? So I take the first one, I convert it to an as character if it's a factor, and then I convert it back to a numeric, okay? What will then happen is it puts it into the type column. This is just type conversions, this as numeric, as character. Doesn't, it depends on how it's put in. Remember you asked me about the factor? If it comes in as a factor, I would have to convert it to a character first, then to a numeric. If it's a straight numeric, I can go straight as numeric, and then I don't have a problem. Once you do that, your new glass, you'll see at the end, let me run it, because I didn't run it, has the new types, 221, okay? And what you could do is, I think where I had it, it was 334, or 344 was original. So basically, my estimations of 334 were 100% wrong from what it actually predicted. Who was right? That depends, right? If I knew mine was right, then the model was horrible, right? If I wasn't sure about mine, then maybe mine is wrong. I have to challenge everything, okay? All right, so that takes care of those 3 lines, 67, 68, 69. Now you have new fields, okay? This function, there are 2 functions in R that bind columns and rows. So R bind says, I want you to take 2 data frames and bind them by rows. So it looks like this. Take one data frame, which is the left one, which is, I think, new glass, and then take the other one and put it right underneath, okay? So if I do that, and I take the new glass and I put the glass underneath, what is it going to be at the top? Which ones? The new glass, which is the 3 observations that I predicted. Could I put them at the bottom to keep the IDs in numerical order? Absolutely. I just shifted them. Why? So that you know they're at the top. It's easier to see when we see them, okay? R bind will bind by row. C bind, column bind, actually binds by column. So I can take one data frame and append another data frame to the right, okay? The only thing that you need to know is if you R bind, you have to have the same number of columns. And if you C bind, you'll have to have the same number of rows. Otherwise, you get a mismatch. Doesn't fill it in, okay? So again, if you do an R bind, it puts one data frame below another. If you do a C bind, it puts one data frame to the right of the other. If you have an R bind, you have to make sure you have the same number of columns, otherwise you get a mismatch. And if you have an R bind, number of columns, C bind, you have to have the same number of, R bind, you have the same number of columns, C bind, you have the same number of rows, okay? Otherwise you end up with a mismatch on both. Okay, so someone's texting. I don't know if that was a question for me or not. So now what I'm going to do is when I ran this, I have a new data set called together. What's this arrow? What's that arrow? What? Equals. Do I need the arrow or can I change to an equal? You need either one. It's the same thing, right? Which one's faster? The equals. Okay. So now what I'm going to do is I'm going to take my quote unquote together, 2 to 10, and I want to compute the distance, this R distance. If you look, R distance gets the Euclidean distance of a matrix or a vector. In other words, it computes the distance of each of the observations from each other. Okay? Does that make sense? I'm going to compute each of the distances. I'm only using columns 2 through 10. I'm not using the type. This is like what we talked about with KNN. It's computing the distance of the items. So I run this. You might get an error, because I already ran this, so I just realized. The RDist is located in the fields package. So if you look in the help and the package is loaded, it will tell you it's the fields package. Okay. If you didn't know that, you can put RDist, RDist R, in R in Google, and the documentation will come up, and in the top left or top right, it will say what package it is. Make sure that you have that package. So I will run this, and now I got this data set called together. 217 observations by 11 variables. Oh, I'm sorry, wrong one. D. D. Look at the size of the matrix. What's the size of this D matrix? What's the dimension of the matrix? How many rows, how many columns? By 217 by 217. Because I have my data set, I am computing how far each observation is from every other observation. So this is a symmetric matrix. This is a symmetric matrix. Okay? Now what I want to do is I want to find out which one is closest. So if we take a look at D, remember the first row. Remember I did my R-bind, right? And I put the new stuff up at the top. So the first 3 observations are my new stuff. How far is my first observation from itself? 0. That's why that first column, first row is 0. I will pause. Do you see that? The first row, first column is 0. Yes?
Sorry, I'm just confused. You run to like line 116, right?
Did you get rid of the lines that I told you to get rid of? You can't be. You couldn't have gotten rid of them because I'm only at 70. Okay, watch this. The rows that you had, look for something called towards the bottom where it says library fields, together R bind glass, new glass, and then this R distance. Start down there. Okay? I only ran the first 3 lines. Okay? It's okay. So this is my distance. Each row, it's a symmetric matrix. Each row corresponds to an observation. Each column corresponds to an observation. The distance between row 1, column 1 is the distance between observation 1 and observation 1 itself. Does that make sense? Okay? It's 0. What's the distance between observation 2 and itself? 0. And that's why you see a 0 in row 2, column 2. Everything else is the computed Euclidean distance of the variables. Does that make sense?
Cool.
kinda like-
After the fields part.
Yep.
I put the field.
Yep.
I'm running line 74.
What's 74?
E equals bar distance together.
Yep.
Running it.
What error did you get?
Together not found.
What?
Together.
Did you run the line that says together equals R bind, new glass, comma glass? Then you run that one. Now watch what happens. Okay? So now this is the Euclidean distance. All I need to do is find which one is the smallest distance between observation 1. Does that make sense? Go with that? So in other words, I want to find, other than 0, which one has the smallest distance? Nope. I got the lines of code. Just give me a second. See this line? Yeah.
Is this leading to, or is this sort of a way to describe the density of the data? Or
No.
okay.
No. This is only the distance. This would be equivalent to a KNN where K equals 1. Okay? This would be the equivalent of a K equals 1 in the KNN. Okay? So this line, okay? I'm introducing this line to introduce you to a couple new functions. I've got this which, I've got this min, I've got et cetera, right? Let's see what it does. This D1 minus 1, okay? What is D1 comma minus 1?
The row and then the column is -1.
What happens if I do -1 in the column?
It's the last column.
Nope. It removes the first column. -1 will remove the first column. So this is the entire D matrix, right? But only the first row with the first column removed. Why am I removing the first column? I'm in my D matrix, I do not have the ID. It's itself, right? I'm removing itself. Okay? So when I do that, it says, get me the minimum of this first row without the first column. Okay? That's what this part does. So I'm going to run min of that. Run. 0.1414. So the smallest distance on row 1 that is not itself the first column is 0.1414. Does that make sense? I only ran that little piece. Okay? I just ran that little piece. Now, what I want to do is I'm going to run this D1 comma blank. What is D1 comma blank? The whole row. I want to know for each of the columns in D, which one is equal to that minimum. I get false, 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 false. Right? There's a true in here somewhere, right there. The which will pull out which one that is. Which one of those is true? So when I run this, the whole thing, number 93. Number 93 is the column in row 1 that has the minimum distance. And then I set it equal to like. Sorry. Run this. Like has number 93. Does that make sense? I will pause. Make sure everybody's got it.
Where we're going.
Where we're going or where I'm at?
No, like, I'm running what you're telling me to run, I'm not getting.
What did you get?
Nothing, I just got the line of code, I don't get the number on.
We didn't get a number under.
Yes, you did, if you get like, you run which, you got 93.
If you just said like equal to it, then.
What? Let me do this carefully. Watch what I do and just follow along here. So if I run, first of all, the min only with the 2 parentheses, I get a number. Do you get that? Let me know if you get that. It's okay. That's why we do this.
I got it,
You got it, right? You got the whole thing or just that piece?
just that number.
Okay. So now what I'm going to do is I'm going to run everything inside that first outer set of parentheses. You see that? See what I'm running right here? You run this, and you get a whole bunch of true falses. Do you get that? So the one that's true is right here. You see that, where I'm highlighting? So what I'm going to do is when I run the which, it is going to tell me which one of those is true. So I run this by itself, just the right side, and I get number 93. You see that? 1 second. You got that? There we go. Okay, I'll pause on that. What's your question?
So when I look at where is 93? Row 93?
It is column 93 in the first row, because that which, this thing here returns a vector, okay, of true and falses. The which is telling you which one is true. The 93rd one in that vector.
That's the smallest one.
That's the smallest one. Yes.
So in other cases using which, does that also create a vector of all the true
It's
values?
going to give you all the true values, correct? Everything that matches, okay? Gives you the index. Now I'm going to use that index. Look at this. Glass, like is the 93, right? So this is going to give me what?
The 93rd record.
The 93rd record in glass. Does that make sense? Okay. I run this, and that is the one that's closer. Actually, I think I'm off by 2, I just realized. Because 93 includes the first 3, you have to add 2. I got to shift it down. Okay? Don't worry about it just yet. I'll fix the code for you.
What's the required?
Because, actually add 3. Because I added 3 columns to the top so that I could do this easier. If I had done it to the bottom, then this would be the exact answer. But I added columns to the top. Just suffice it to say that if you've got the right number, 93, and you pull this, this is telling you that this number, we'll just deal with it for now, 93 is the observation that is the closest.
To what?
To the observation number 1.
Oh, I see.
Okay?
So it's the neighbor.
Correct. This is how you would get the nearest neighbor. Okay? Does that make sense? This would be equivalent to k equals 1. The only mistake that I made here that I just realized is that it's the 93rd column, right? But the first 3 columns were the new observations. So the real data starts at 4. So you have to add 3 to 93. So 96 in this case, and I'll rewrite this for you. I'll put it out there for you. But this is actually going to be like plus 3. And that's type 2. New glass 1, which was the one I was comparing, is that one. So what does it look like? Well, look at your RI, 1.51. Look at the RI of new, I'm sorry, 1.51 here. Look at RI, 1.51. That's of the new observation. 13.36, 12.55, 3.43, 3.4, and so forth. The only reason we're doing this is to show that the Euclidean distance is equivalent to a KNN equals 1. You could rerun your KNN, K equals 1. You should get the same answer. Yes?
So when we ran the plot before, we were only plotting 2 dimensions.
Correct.
But we're comparing the distance with all of them.
That's correct. You can't do that on a plot. You have to do that mathematically. Okay? That's how KNN works. I can pass in new data. I can reclassify, figure out what the numbers are. What you would then do is if I had like 10 of them, right? Let's say you had 10 new observations. Should I do the KNN and then add 10? Should I do the KNN, add 1, then KNN, add another 1, then take that, add another 1, and redo them. Do them one at a time. That is all based on when you want these things recomputed. Does that make sense? Any questions? Good stuff. Yeah, this is killing the brain cells. Any other questions? Yes.
I don't think I'm getting why it's returning an entire row.
You see where it says, wait, which part?
Just conceptually, like I get that the formula is returning the whole row, but are you doing 1 point?
So what I'm trying to do is when I took the first 3 and I put them at the top of this data set and I computed all the distances, right? What I'm checking for is this. I'm checking to see that first row, which one was the closest. So it's going to be the smallest number.
Closest to what?
Closest in Euclidean distance. So remember that observation, if it was only 2 points, right? If it was only 2 variables, it'd be 2 by 2. It'd be square root of a squared plus b squared, or whatever the difference is. x1 minus x2 squared plus y1 minus y2 squared. Take the square root and you get a distance. So remember that first chart with the purple and the 2 points? We're computing those distances. That's what this does. It just does it in our case, 2 through 10, 9 dimensions. Okay? So what I'm doing is I'm going to now traverse all of those dimensions, all of the observations, because it computed all the distances. Which one is the smallest? So number 93. So observation 93 is the closest distance to 1. So if it was KNN equals 1, whatever 93 is what I vote.
You know how like in the data set that we have, that we just created, the distance, you can filter or like organize data to see it from smallest to you do see that in grade.
Yeah. Pretty cool when stuff works, right? Okay, any other questions?
RI, NA, NG, about that stuff.
Does what?
You type the first two tests. The RI, NA, NG.
Yeah.
We worry about that, or we just,
Those are just the values. RI and NG, those are the values. I'm only showing you what it would look like if you did a comparison. But distance-wise, these are the two closest ones.
what?
What? To row 1, correct. You could then run it for row 2, which is the next group, okay? Notice how I changed the 1s to 2s? Then you can run it for the third one. Yeah.
Shall we just remove the first 3 columns because they are all new observations?
You can remove the first 3, yes, you can do that.
Yeah, because if,
But you have to compute the distance first, and then you remove the 3 columns.
I mean, if in the matrix D, if the
That's correct. You're right.
smallest.
Yeah, you just remove the first 3 columns. That make sense? Any other questions? With this, you should be able to do one of the 2 missing problems. Next week, we will do the last problem for your midterm. Okay? All right, so here's what I'd like you to do, because it's 7:50. I'll stick around, obviously. I'll stick around as long as people need. And you might want to talk in your groups about where you're heading, because right now you have 1, 2, 3. You have 3 primary techniques, and you can do some other things with your data. So at this point, you should be halfway done with your project, getting ready to dot the I's and cross the T's, and you've already got your data set done. It's in multiple data frames. Yeah, everybody's like, oh yeah, we're way there. So far ahead, doesn't matter.